Jupiter stands as a colossal celestial object, dominating our solar system with its immense proportions and gravitational influence. As the fifth planet from the Sun, Jupiter reigns supreme in terms of planetary dimensions, establishing itself as a benchmark for comparative planetology and exoplanet studies. This gas giant's sheer magnitude shapes our understanding of planetary formation processes and provides crucial insights into the evolution of our solar system. The planet's imposing presence creates a natural laboratory for studying the upper limits of planetary size and the threshold between the largest planets and the smallest stars. Jupiter's dimensions are truly staggering when compared to Earth and other terrestrial planets. The gas giant boasts a mean radius of 43,440.7 miles, 69,911 kilometers, establishing it as approximately 11 times larger than Earth's radius. This volumetric mean radius places Jupiter at nearly 11 times, 10.973 to be precise, Earth size when averaging all dimensions. The scale becomes even more impressive when considering that Jupiter's diameter is about a tenth of the Sun's diameter, positioning it as an intermediate-sized object between terrestrial planets and our star. Jupiter's massive size becomes particularly apparent when visualizing its circumference. If one were to walk around Jupiter's equator, they would travel approximately 272,946 miles, 439,264 km, which is more than 10 times the distance required to circumnavigate Earth. These dimensions underscore Jupiter's status as not merely larger than Earth, but belonging to an entirely different class of planetary body. Jupiter's appearance deviates significantly from a perfect sphere due to its rapid rotation. The planet completes a full rotation on its axis in slightly less than 10 hours, making it the fastest rotating planet in our solar system. This swift spin generates substantial centrifugal forces that cause the planet to bulge noticeably at its equator, creating what astronomers classify as an oblate spheroid. The equatorial diameter measures 88,846 miles, 142,984 kilometers, while the polar diameter is considerably smaller at 83,082 miles, 133,708 kilometers. This difference results in an equatorial bulge extending 9,276 kilometers, 5,164 miles, beyond what would be expected in a perfect sphere. Jupiter's ellipticity value of 0.06487 is remarkably high, approximately 19.36 times greater than Earth's ellipticity. This pronounced oblateness is readily observable even through amateur telescopes, providing visual confirmation of the physical effects of Jupiter's rapid rotation rate on its overall shape. Jupiter's mass substantially exceeds that of all other planets in our solar system combined, weighing in at approximately 1,198.13 x 1024 quark. Jupiter is 317.83 times more massive than Earth. This immense mass accounts for more than 2.5 times the combined mass of all other planets in the solar system. Despite this enormous mass, Jupiter remains slightly less than 1,000th the mass of the Sun. What makes Jupiter particularly interesting from a physical perspective is its relatively low density of 1,326 km3, which is only about 24% of Earth's density. This low density stems from Jupiter's composition as a gas giant, consisting primarily of hydrogen and helium, rather than the heavier rocky and metallic materials that constitute terrestrial planets. The contrast between Jupiter's enormous mass and relatively low density highlights the fundamental differences in composition between gas giants and rocky planets like Earth. The volume encompassed by Jupiter is truly difficult to comprehend in human-scale terms. Jupiter's volume measures approximately 1,431,281,810,739,360 cubic kilometers, which equates to 1,321 times the volume of Earth. This enormous volume would be sufficient to contain more than 1,000 Earths. Similarly, Jupiter's surface area, measuring at the 1 bar pressure level, typically considered the surface for gas giants, spans about 6.219 x 10 square kilometers, or 23,713,737 square miles, which is 120 times greater than Earth's surface area. These enormous proportions help explain why Jupiter can generate such powerful storms that can persist for centuries, the Great Red Spot being the most famous example. as the available atmospheric canvas for such features is vastly larger than anything possible on Earth. The immense surface area also creates an extensive region for absorbing and reflecting solar radiation, contributing to Jupiter's distinctive banded appearance. Jupiter's significant mass has led astronomers to adopt the Jupiter mass, MJ or MJ-up, as a standard unit of measurement when discussing especially massive objects like brown dwarfs and exoplanets. When astronomers discover planets orbiting distant stars, they often express the planet's mass as a fraction or multiple of Jupiter's mass. For example, the exoplanet HD 29458bi has a mass of 0.69 mj, while the brown dwarf Gliese 229bi is substantially more massive at 60.4 mj. This standardized unit helps astronomers quickly communicate the scale of newly discovered objects and place them within the known spectrum of planetary and substellar masses. The widespread use of Jupiter mass as a reference unit demonstrates Jupiter's importance as a benchmark for understanding cosmic objects that exist at the boundary between planets and failed stars. Jupiter approaches what theoretical models suggest is the maximum possible size for a gas giant planet of its composition. Counterintuitively, if Jupiter were to gain additional mass beyond roughly 40% of its current amount, its diameter would actually decrease rather than increase. This paradoxical relationship occurs because the additional mass would create greater gravitational compression at Jupiter's core, causing the planet to contract despite containing more material. Jupiter would need to gain approximately 75 times its current mass before it could initiate hydrogen fusion and become a star. This places Jupiter well below the threshold needed for stellar ignition, yet its diameter is remarkably close to that of the smallest red dwarf stars. This similarity in size, despite vast differences in mass, illustrates the complex relationship between mass, gravitational compression, and volume in large celestial bodies. Jupiter's enormous mass generates substantial gravitational pull, with an escape velocity of 59.5 km/s, 5.32 times Earth's escape velocity. This strong gravitational field has profound effects throughout the solar system. Jupiter is the only planet whose barycenter with the Sun, the center of mass around which both bodies orbit, lies outside the volume of the Sun itself, although it remains within 7% of the Sun's radius. Jupiter's gravitational influence likely played a critical role in the early formation of the solar system, as its inward migration affected the formation history of other planets. Today, Jupiter's gravity continues to shape the asteroid belt and influence the orbits of numerous smaller bodies throughout the solar system. The planet's immense size creates a significant gravitational well that captures and holds its 95 known natural satellites, vastly exceeding Earth's single moon. Despite its seemingly permanent appearance, Jupiter is gradually shrinking over astronomical time. Due to the Kelvin-Helmholtz mechanism operating within its contracting interior, Jupiter shrinks by approximately 1 millimeter per year. This contraction releases gravitational potential energy as heat, causing Jupiter to radiate more energy than it receives from the Sun. When Jupiter initially formed, it was considerably hotter and approximately twice its current diameter. This continuing contraction represents the very slow cooling and condensing of the planet over billions of years. Though imperceptible on human timescales, this ongoing process demonstrates that even objects as massive as Jupiter remain dynamic, evolving entities within our solar system. Jupiter's remarkable size and scale establish it as a planetary behemoth that defies easy comparison with terrestrial worlds. From its vast equatorial circumference to its enormous mass and volume, Jupiter represents a scale of planetary formation that dwarfs the inner rocky planets. Its position at the upper boundary of planetary size, approaching but not reaching the threshold for stellar ignition, provides valuable insights into the formation processes of both planetary systems and stars. Jupiter's colossal proportions continue to serve as both a standard for astronomical measurement and a subject of ongoing scientific investigation, helping us comprehend the tremendous diversity and scale of cosmic objects in our universe.